We're going to start with Chapter 1, Bushong, and if you haven't read through the little penguin thing over on page 3, basically, you know, the short and long of it is that Bushong's a character. I don't know that he'll ever do speaking engagements anymore. He's gotten kind of old. But he's a funny guy, he really is, and he kind of looks like a penguin there. So the caricatures that you see throughout the book are caricatures of Stewart Bushong. He's got a great big walrus mustache, and if you're ever bored and you want to look up there used to be a prominent surgeon that, I don't know if he was Texas Surgeon General or if he was just a person that was well respected, but he used to do a segment on TV, and his name was Red Duke, R-E-D-D-D-U-K-E. And Stewart Bushong looks an awful lot like him. So he doesn't have Red Duke's voice. Red Duke sounds not like a surgeon, but like he just got off of a plow mule. But anyway, I think Red Duke's long deceased. But at any rate, I'm guessing this Elizabeth Shields is going to be the editor of Bushong's book after Bushong retires. So, but the short and long of the penguin there is that you only have so much room in your head before you run out of room. Okay, so the story is that there's this iceberg that all the penguins want to get on, but in order for another penguin to get on the iceberg, another penguin has to get off. Okay, so what his point then is that there are certain things that are more important than other things, right? So, you know, pick the things that you're going to fill up your iceberg with and forget about some of the other things. So I'm not saying that you go through the book and the only thing that you focus on are what has a penguin in it, but that's what he describes as being, you know, a major concept. So focusing on those major concepts is potentially a good idea, but you know, if you think your test is just going to say that mass is the quantity of matter as described by its energy equivalence, no. You got to know more than that, but that's a concept that you need to be familiar with. So that's what the penguin is all about. What we're going to do today is we're going to go through the nature of our surroundings. We're going to talk about matter and energy. We're going to talk about the different types of energy specifically. And then we might get into the sources of ionizing radiation, but we're not going to get past that. So we're not going to go past page 6 today. We're going to spend quite a bit of time on matter and especially energy, and how we use matter, not so much, but energy in transformation in order to create X-rays. So we're going to go through all the different types of energy, and then I'm going to tell you how we use each one in diagnostic, mostly diagnostic radiology. One, not so much. So, nature of the surroundings. Where do I put my notes? Again, I don't teach from PowerPoints in this class, so I'll scribble down notes and bring in notes just to make sure that I hit all of the major topics I want to talk about. So nature of surroundings, if you look around yourself, you see two things really. You break everything down into two things: matter, energy, or possibly matter that's using energy, right? So look around the room, you see lights, you know, and the light emanates lights. The lights emanate light. So you've got this stuff coming out as pure energy, yeah, sort of. We'll talk about that later. But for our purposes, we're going to say it's pure energy at this point. We're going to, again, get deeper into that around chapter 3 or 4. So it's an example of energy. And then you've got everything else that you can physically see because of that energy, and that's matter. Now, sometimes we're going to have sort of a combination of the two. Like you're kind of a combination. You're matter that uses energy, right? So even though those are two separate things, you're both are at work in you. We'll talk about that here in a minute. So matter, the distinguishing characteristic of matter is that it has mass. Okay, it sounds like they're the same thing, and they kind of are. But they have mass and it occupies space. You know, there's one person per chair here because you're made of matter, right? You can't both occupy unless somebody sits in a lap, and then you're not really sitting in a chair, you're sitting on somebody two pieces of matter cannot occupy the same space. So it occupies space and it has matter. So, or it has mass. So what is mass? When you think of mass, what do you think of? Weight, right? But is it the same thing? It's not really. We use it to describe that. You know, you look on, I don't know, let's say a bag of sugar, box of salt, whatever. You want to know how much is in it, what do you look for? You look for the weight, right? You look for the weight of it, but what's inside of it? Salt, which is matter, right? So, you know, table salt, sodium, you know, fundamental elements are what make up matter, right? So it's not the same thing as weight, and I'll use this example. If you took a balloon that had no air in it, and you threw it on a, you know, you just tossed it, what would happen to it? It'd fall to the floor, right, it'd fall to the floor. Why? This is the question for this class, is why? You know, you gotta why until you get to something that you can't why anymore. Why does it fall to the floor? Gravity, gravitational pull. So gravitational pull is really the effects of, or the weight is really effects of gravitational pull on matter, okay? So you pick up the balloon and you blow it up and you throw it again, what happens to it? Ish, yeah, it floats ish, you know, until it hits the floor, and it bounces a couple of times and it's still on the floor. So what is matter? It has mass. It has mass, right? So, and what is mass made up of? Individual little bitty pieces of stuff that everything is made up of, and that's atoms. So mass has atoms, right? So regardless of what kind of mass we're talking about, it has atoms. Okay, now let's take that same balloon and we fill it up with helium. Is helium, where do you find helium? I mean, in a textbook, where do you find it? It's in your textbook. Periodic table, right. It has the atomic number of 2. It's in a periodic table. It is an atom. Okay, so is it mass? It's absolutely mass. It occupies space, has mass, even, you know, it's matter. Even though it's so small that you can't see it, it's still there. But you fill up that balloon with it, and what happens with the balloon? It floats, right. So I go all that way to say, is matter and weight the same thing? No. The answer is no. If helium is matter, it has mass, and it floats, then gravity isn't really affecting it the way it does most things, right? So, not necessarily the same thing, even though and that's as deep as I'm going to get into that. There are questions on the test, is matter and weight the same thing? And the answer is no, it's not. You know, if it's true false question, it's a statement that says matter and weight are the same thing, your answer is false. It's not, right? Are we going to get any more hung up on it than that in this class? And the answer is no. We're going to use them interchangeably pretty much. Even the most fundamental measure of matter is a kilogram. And we still, yeah, mass. It's a kilogram. And we still use that, you know, as a measure of weight, right? So, you know, for those of you who have ever gone to the gym, what do you see on the plates if you're, you know, looking at free weights? You see pounds and kilograms, right? So we still use that. So it's not, you know, not something to really get hung up on, but by the strictest definition, matter and weight, mass and weight aren't the same thing. Okay? All right, so there are, you know, specific measures of it, but they're not the same thing. So other examples would be, y'all are all young, and I use this every year because it's so awesome. Y'all are all, you know, pretty young, and you probably have kids in your future. And if you do have kids in your future, Space Camp in Huntsville, Alabama, I cannot recommend it enough. But if you send your kids to Space Camp, don't send them, take them when they're like 6 years old, because you can go too. It's like a long weekend, and you get to play on the simulators, and it is great. Okay, so put that on hold for just a second. You've seen videos of people walking on the moon, right? How do they walk on the moon? Yeah, they bounce, right. And the reason for that is because the gravitational pull on the moon is 1/6 of what it is here. So, you know, Bushong goes through the example that if a 200-pound person was on the moon, you know, he tells you exactly, or 200 kilo, what did he say, pound? But at any rate, you're going to weigh 1/6 of what you do here on the planet, on Earth. Okay? If you were to go to Jupiter, it'd be 2.53 times as much. If you were on the sun, it would be something like 28 times as much, okay? So what's the difference between the Earth and Jupiter? And I'm giving it to you here. Yeah, size, it's mass of the planet, so the gravitational pull is greater on those planets or that star than what it is here, okay? So again, it's a gravitational pull on a mass. U, the mass, it's a difference in gravitational pull. All right, so back to space camp. One of the things that they do at space camp, and one of the ways that they train astronauts is with what they refer to as a 1/6 chair, okay? That sounds complicated, doesn't it? It sounds high-tech, 1/6 chair. What's the 1/6 chair? It is, you can build one at home. Very simple. Oh, and by the way, I stopped by Walmart this morning, got some markers. So what the 1/6 chair is kind of an overhead rail system like what you would see in the X-ray lab. So if you're in lab today, you know, walk in and look up at the ceiling. What you see is two sets of rails that are mounted perpendicular to each other, so you can take that X-ray tube and put it anywhere in the room that you want it to go. Very, very versatile. In the portion of the space camp where they have the 1/6 chair, they have something similar to that. It's a rail system overhead, and suspended from the rails are all these springs. Those springs are attached to this thing. They call it a chair, but in reality, it is the cheapest looking thing you ever saw. Your tax dollars at work. So what it is this, it's like a board covered in vinyl that comes down and makes a right-hand turn, and you sit on this thing with your legs dangling down like that. This guy's got really short legs, like that. And then you know, your gravitational pull pulls the springs until you can actually touch the ground. And what that's supposed to do is remove 5/6 of your body weight. Does that make sense? Mm-hmm. So suddenly the pressure that your feet are putting on the ground equates to 1/6 of your body weight, right? And then they tell you, they put you on this thing that's a bunch of uneven ground, kind of like and it's not that dramatic, but it's uneven ground. They tell you, okay, you want to walk from this to that end. Ever seen any old cartoons where, like Scooby-Doo or something like that, where the dog takes off running and he goes before he can grab traction? That's what you do on that. You cannot walk. You just can't. So the reason they do that hopping is because they can get gravity and then hop and land. You know, you jump from, let's say, the tailgate of a pickup. We're in Texas. Anybody not jumped off a tailgate in Texas? You know? Okay, we got to take you out to the parking lot. At my age, you don't jump anymore. It hurts. So I kind of step off. But at any rate, jump off, and what happens? You're jumping from a height. What happens? You get the acceleration of gravity, and you have impact, so it kind of sucks you down, and you can jump, and you can travel that way, but you can't walk on the moon. You just can't. There's not enough weight. There's not enough gravitational effect on your mass to give you the traction to walk on the moon. Okay? So, weight, mass, the same thing? No. But again, this class is as deep as we're going to get into that, and as specific and I don't know, precise as we're going to get about that. So, so the fundamental unit of mass is a kilogram, and mass can be transformed into one state or from one state to another. and Bushong talks a little bit about water. And, I'm going to refer to Bushong an awful lot because this lecture comes out of Bushong. So how do you prepare for this class? You reach Bushong, right. So water it's a weird, fascinating substance. We take it for granted, but it's a weird thing. Most of the time you heat something up and what happens to it? It expands. Most of the time you cool something down, what happens to it? It shrinks. Water expands in both cases. You freeze water, you put your water bottle, and I'm not talking about your expensive metal water bottle, but you put a water bottle in the freezer and what happens to it? You come back and look at it and what happened? Yeah, the bottom, you can't set it down anymore because it's a ball, right? So it expanded. If you put cans of anything in the freezer, what might happen? It'll explode, right? It'll expand to the point that it explodes. So another thing that when you're looking at solid things versus not solid things, you have a tendency to think, okay, that thing is solid, it's going to be heavy, right? Well, what happens to the weight of water when you freeze it?
It gets heavier.
What's that?
It gets heavier.
You would think so. It gets lighter because if you drop it in your cup, you drop one water cube in your cup, what's going to happen to it?
It floats.
It's going to float. So it gets bigger and it gets lighter. Now we heat the water up and it becomes water again. We heat it up enough though and it starts to boil, but what's coming out of the top of the pan that you're boiling it in? Vapor, right. So as it vaporizes, it expands again. Okay, so we expand enough of it and it becomes cloud, right? It's very expansive, it condenses and it rains. If you could take an ice cube, melt it, right? Then you would have the same quantity of matter in the ice cube as you had in water. Now you heat the water up, it vaporizes, it goes up and you can collect all that, cool it back down and turn it back into water. You should still then have in all three states the same quantity of water. So was the weight the same in all three of those? No, it was heaviest when it was water, got lighter when you froze it, got lighter whenever you boiled it, and it also got bigger whenever you froze it and boiled it. So three different states, the same stuff, same quantity of matter, same mass, different states, right? So again, weight and mass is not the same. Okay, so everybody good with matter? Okay, so we got a lot of different types of energy to talk about. And just running through those, starts on page 4. You've got potential energy, kinetic energy, chemical energy, electric energy, thermal energy, nuclear energy, and then electromagnetic energy. So I'm going to start over here. Potential. When you say somebody has potential, what are you saying about them?
They can do something.
They can do something, right? You have the potential to be, a great scientist. Does that mean you're right now a great scientist? No, you're not. You might be, I don't know. But the word potential implies that you haven't realized, your full potential. You haven't become what it is you have the potential to become. Okay? Then we have kinetic energy. Kinesiology, study of movement, right? A lot of people have kinesiology degrees. Kind of flooded the market with that. Well, I'm going to be a personal trainer. Probably not. We have millions of people with kinesiology degrees that are, flipping burgers. So anyway, study of motion, kinesiology, study of motion. So we got motion here. So chemical energy. And then we've got electric, thermal, and nuclear and electromagnetic. And it becomes becomes much more difficult to write, at waist level. All right, so potential energy. We talked about that. It's you say somebody has potential, and they have the ability to become something or do something, right? And energy is the same way. You have potential energy. It's the energy of position. Because something is placed in a certain place, it can become useful. We can use it for work. Okay, and it doesn't necessarily just have to be placement, but it can be, it's the energy of position, it's stored energy, it's unrealized energy. If we release that potential, it can do something, okay? So, you have a great big rock, and the rock is positioned on the side of a mountain. It has energy, just by virtue of its position. If enough water washes out from under it, what's going to happen to the rock? It's going to tumble down the hill, right? So then it becomes kinetic energy, all right? So potential energy is just the energy of position. Nothing's happening at this point. A mousetrap, you pull the I don't know what you call it, the spring part, or the arm back to put tension on the spring on the mousetrap, and you lock it in place, then it has potential. It's not doing any work yet, not until the mouse comes to the bait stick and gets some of the goodies that you put on there that it actually snaps and it does actual work. So I kind of talked about the cartoons. So I show this every year. I think it's hilarious. I think it's a great demonstration of the difference between kinetic and potential energy. So we're going to take a look at it. These are the kind of cartoons I had growing up. We had great cartoons. Cartoons. Yeah. So cartoons now are just dark. No, cartoons shouldn't be dark. So this is the Roadrunner and the Coyote. Okay. So the premise of the cartoon is that the Coyote spends millions of dollars buying these traps and things to try to catch the Roadrunner, where he could have just ordered Domino's and have plenty to eat, but he doesn't want to do that. He wants to catch this Roadrunner. So in this case, he's got a big spring tied to a rock, and the spring is going to, it's going to propel him to a point. Yeah. There we go. Okay, so here's your mousetrap. That's a big rat. All right, so let's back this up. What kind of energy do you have there? That's potential energy, because he's already pulled this thing back, the arm back, and we've got tension on the spring. We got bait there. You don't see it released, but you'll see it in action here in a minute. So it snapped. The mouse is not all that happy. So he takes and he puts tension back on the arm, snaps it onto the Coyote. So right now we have no potential. We've already got that. The only potential we have is this monstrous mouse and what he wants to do to that Coyote. Pulls it back, releases it. So potential followed by kinetic. And so here's the spring. And this one goes over and over and over again. What do we have? Potential. We have potential. We have tension on the spring, a lot of compression there. We have tension on the spring. There goes the Roadrunner. He picks his feet up. Right? Must be memory metal. It's not doing anything yet, but kinetic energy. So he's flying, right? He's chasing the Roadrunner. He couldn't catch the Roadrunner, so he cheated. He got this thing. So now he's got nothing under him to block him, right? And just like the rock on the side of the cliff, he's got potential energy because he's gonna fall, right? He's still attached to the spring. He didn't come disconnected to the spring, so you know he's got limited potential. You know, what do you think might happen, you know, once the spring fully extends?
He's gonna snap back.
And maybe pulls him back, right? Maybe just stops him. Oh no, not in this. So he falls. Kinetic energy. He hits the ground. He's pulling a rock. And again, we've got potential energy, kinetic energy. So, potential versus kinetic energy. I think that's a fun video. All right. So, get rid of that. So everybody knows the difference between potential and kinetic energy. Energy of position. You're not doing any work yet. Okay, energy of position. Kinetic energy, energy of motion. Okay, so what is chemical energy? Energy from chemical reactions, right? So Bushong uses the analogy of you eating food. It's a good analogy. You eat food, your body breaks it down, and it converts it to energy, right? Yeah. So you don't eat enough, and you kind of feel a little dragged. I really don't recommend you drink energy drinks to bring that back up. You need food. You need actual nutrients. So the nutrients provide energy for you, and you can see that in everything. You know, I mean, the trees outside, the grass outside pull stuff out of the ground, nutrients out of the ground, and they use those nutrients for photosynthesis to grow the tree, to grow the grass, all that stuff. Everything uses chemical energy. You've also got chemical energy that you carry around with you everywhere you go. Where do you see that? Technology works off of electricity. And are you plugged into the wall? No. So what do you have to provide you that electricity? Batteries, right? Batteries, just a form of a source of electric power, right? So batteries. I'm going to say chemical reaction. Batteries. For our purposes, batteries is a better example of chemical energy than what is, you know, for the lecture. Really, nutrition is better for us, but for the lecture, then the battery is a better example. So what is electric energy? Well, we just kind of touched on that. It's electric energy. Electric energy, we can power things like your laptop, like your tablets, your phones, the lights, all that. And what it is movement of electricity. Well, what is electricity? Electrons. It's movement of electrons. So you don't, when we get into the chapter where we're talking about electricity, what we're talking about in electricity is going to be movement of electrons. You're not moving protons, neutrons, quarks, or any of that kind of stuff. You're moving electrons. We'll talk about why that is later on, but moving electric charges specifically electrons, right? So, anybody ever go snow skiing?
Snowboarding.
Huh?
Snowboarding.
Snowboarding? Same thing. So, what do you wear to stay warm? At least the first time you go. Thermal underwear, right? Yeah. First time I went, you know, I'm from East Texas where humidity is high. Had no idea 25 degrees in Colorado was totally different than 25 degrees in East Texas. 25 degrees in East Texas, you are miserable. And I wore long johns, thermal underwear. What else did I wear? I wore, coat, and I had on, I think, a wool shirt. First trip down the mountain, I got to get this off, right? So thermal has to do with heat, right? Thermal energy is heat. And we also say that it's kinetic energy on the molecular level. So it's movement of molecules. A little bit more on that here in a minute, but if your molecules bouncing around, knocking off of each other, you're going to create heat, okay? Nuclear. We don't really use nuclear so much in diagnostic imaging unless we're getting our electricity from a nuclear power plant. And diagnostic imaging, what I'm talking about in diagnostic imaging, when I refer to diagnostic imaging, that's X-ray. Okay, it's the portion of the imaging department that is X-ray. All modalities are diagnostic. Okay, so it's a little bit misleading to just call X-ray diagnostic imaging, where MRI is diagnostic imaging, CT is diagnostic imaging, nuclear medicine is diagnostic imaging, but we call X-ray diagnostic imaging, okay? But nuclear medicine is an imaging modality that works in a totally different way from X-ray. So with X-ray, what we do is we create an external beam of radiation, we pass it through the patient's body to create a shadow of the anatomy that's inside of the patient. It's mainly, we do some exams for physiology, but it's mainly anatomical. The integrity of the bone look good, is it broken, those sort of things. With nuclear medicine, what we do is we put radioactive isotopes inside of the patient, and we measure how much comes off of the patient. And if the patient has a pathology of some sort, it'll either put off too little or too much radiation. Okay, so we do use it in imaging, but not in diagnostic imaging. We use it in nuclear medicine. Okay, so we're going to kind of circle that one because we're going to, in our example that, I'll talk about here in a minute, that's just going to be the power plant. We're not really using it in diagnostic imaging. And then finally, electromagnetic. So electromagnetic, just breaking down the words, you've got electro and magnetic, and it is any kind of energy that exhibits both of those characteristics. So any kind of energy that behaves in a lot of ways like light. Now there's a wide spectrum of those type of energies. Okay, so you got microwaves, radio frequency waves, infrared radiation, you've got X-rays, gamma rays, and then you've got your visible light too. So all of those are different types of electromagnetic radiation. You need to familiarize yourself with the word and understand that it's it's what X-rays are. It's electromagnetic radiation, but we're going to talk more in depth about it later in the semester. So then the question becomes, what does it all mean? Why are we talking about this? Funny you should ask. So if we get our power from a nuclear power plant, then we've used our nuclear energy, right? Again, in imaging, we're going to use that in just that, nuclear medicine. So we get the power, and it goes from the power plant to the telephone pole, where we've got that thing on the telephone pole that we refer to as a transformer. Very good. It's a transformer. Y'all didn't know we were going to draw this again, did you? So we've got that. We're not going to draw all the components to it. We got that, and then it goes into the imaging system. And what's the first thing it gets to, sort of? And I'll explain the sort of later. It's another transformer that we refer to as a auto transformer. Very good. An auto transformer is a type of rheostat. We call it a rheostat because we can increase or decrease the power, right? This is kind of like a dimmer switch on lights. So if we feed that alternating current, then what we're going to do is we're going to set up a changing magnetic field. And if we plug into the opposite side of it, we're going to also get alternating current on the other side of this. Okay? So alternating current, I can't seem to make it go in the opposite directions over here. Okay, so it comes out of that and it goes into a different type of, which is the exact opposite of that type of transformer, where we have a few squiggly lines on one side and a whole lot on the other side. What that does is it sets up a changing magnet. We use alternating current to set up a changing magnetic field in the very good primary side of the step-up transformer. And if we move a secondary coil that has a whole lot of turns on it, squiggly lines on it, that would be our secondary side. And so we set up a changing magnetic field here to create a alternating current of higher voltage or amperage over here? Voltage. It goes from voltage to kilovoltage, right? Now that comes out of that. It's going to go through something else, but eventually it's going to go inside of the X-ray tube, which it's a diode, which means we have two. Exactly, an anode and a cathode. And our tube is going to look roughly like that. Okay, so we heat up the filament here, with this lower circuit. I'm not going to draw all the components of the lower circuit, but anyway, we've got all the components of the lower circuit around in here. And the whole purpose for that lower circuit is to heat that up, okay? To get to a point where we boiled off electrons, and we call that, bingo, thermionic emissions. We get thermionic emissions. And we also refer to that as the formation of a space charge or electron cloud, either one. At the same time, whenever we push a button, the prep button on our control panel, what happens over here? Starts to spin. It rotates because we call that a rotor, exactly. So it rotates. All right, so we've got all of that. So where do we plug all this stuff in? Well, what are the different things that we call kVp? You remember? kVp equals kilovoltage peak. Yeah, that's what that stands for, kilovoltage peak. And just so you know, when we make an X-ray beam, let's say we set 100 kVp on our X-ray beam, at the point of impact on the anode, you're not just getting 100 kVp. You're getting from effectively 0 up to 100 kVp. That's why it's kilovoltage peak. It's the highest energy X-ray photon we're going to create. Okay? We're really going to hammer that sometime this semester, but we're really going to hammer it next semester in filtration and what filtration does in our imaging system. Okay? So that's a peak energy. It's kilovoltage peak, but we also call it other things, and that is electric, wait for it, potential. Potential energy. It controls the power of the X-ray beam. It controls the penetration of the X-ray beam. You're looking at a lot of P's here, right? It is the potential difference between the cathode and anode into the X-ray tube. Okay, so with electricity, what you have are two opposite charges effectively. So you have a negative end and a positive end of something. So if you're looking at a circuit, you've got a positive end and negative end. So what we've got is over here, when we get to a point of thermionic emissions, what do we have a lot of? Thermal energy. Oh, very good. I wasn't going there yet, but thermal energy is hot, right? But what have we stored on and around that filament? A lot of electrons, right? So what are the charges of electrons? Negative. So this is going to be a negative end of our X-ray tube. And this is going to be, therefore, the positive end of the X-ray tube, right? So the more negative charges that we have, by default, the greater the difference between those two ends. Okay? I also said, though, that this thing down here, okay, I gotta draw it now. So it's got a lot of squiggly lines and not so many squiggly lines. What did that do to our voltage? Brought it down, right. So we use very low voltage to keep the electrons from jumping across the tube before we're ready to. Okay, so when we hit the prep button, we spin that, we activate this, we heat that, we're not making X-rays. You can spin that all day long if you want to. You shouldn't, because it tear up your x-ray tube because you're creating nothing but heat and a little bit of light, okay? So you get to the point of thermionic emissions, but you're not taking any x-rays. It's not until you push the exposure switch that the electrons jump across. So if we have electrons here and we have a positive anode here, what do we have? Are we creating x-rays? No, but we have the potential, right? So kVp controls our potential. That's our tube potential, okay? We're not creating x-rays until we activate this and we apply the high kVp. Now the electrons jump across the tube, now they're moving. So we have, second, kinetic. We got kinetic energy, right? So they're gonna hit this thing really, really hard, approaching the speed of light. Maybe, you know, if you're using 120 kVp, maybe a third of the speed of light. If you're using 50, it may be a fifth of the speed. They're moving really fast. Don't get tied up in, you know, exactly how fast. Fast. They're going fast, right? The higher the kVp, the faster they move. So that's pretty much all you need to know is just one more fast. They're going. All right, so they hit that. Do they just stop? No, but they slow down. And we have two ways of creating x-rays. One is characteristic, where you knock an electron out. What's the other way? Brems, which means what? Breaking. Right, so they slow down, they enter the system again, and you've still got electricity to complete the circuit, okay? Now, why did we create heat there? What's the definition of thermal energy? It's heat, but it's heat on the atomic level, right? So we got a lot of electrons bumping into each other, aggravating each other, creating heat. So anytime we see, or anytime we send electricity through a circuit, we really create two things. One's a magnetic field. We'll get into that later on, but the other is heat, okay? So, do we have potential energy? Yeah, right before we push the kVp button, once the kVp button is mashed, we go with kinetic energy. We're using moving electrons to create thermal energy to eventually create x-rays, which are a form of electromagnetic energy. Now, the only thing that we've missed here is our chemical. We dealt with the nuclear here, right? But we do, where'd it go? Chemical energy as well. Anybody been on a portable?
Yeah.
Okay, good, very good. Did you have to plug the portable in before you made the exposure? No. Why do you think that is?
It's got charged batteries in it.
It's got charged batteries in it. Now, here's a safety tip for you. Again, an awful lot of what I communicate in class is that are stupid stories and warnings for you and things to avoid are because I did them. Ran over my own foot with a portable one time. Ever picked up a battery? I don't mean a D-cell. I'm talking about like a car battery. That thing is full of them. Okay, so if you went on portables, you probably got on the elevator. Did you feel what happened to that elevator when you got on there? Yeah. You go, right? Don't run over your foot with a portable. I was lucky enough that I just caught the soft tissue on the lateral side of my foot. Blood blister all the way down it. If I'd have gone over my toes, I probably would have broken my toes. Don't run over your foot with a portable. Don't run over anybody else's foot with a portable, okay? So, chemical energy. Those work off of batteries, so we've got that checked as well. We use them all. I'm sure there are all different other types of energy, but those are the ones that we use in diagnostic. All important, some more important than others. Certainly the electric energy is great. We have to have the electric energy, we have to have the thermal energy, but we get to a point where we can't stand the thermal energy anymore. As a matter of fact, two things about thermal energy. One is, I'm just going to say heat instead of thermal energy because it's easier. One thing about heat is that it's the main thing that's going to kill your x-ray tube. Okay? So, with an incandescent light bulb, we put enough heat on that, what's eventually going to happen to it? It's going to burn out. It's going to burn out, right? So also your rotor has to rotate on something, and what it rotates on are bearings, and if those bearings get too hot, then it's going to, they're going to, yeah, they're going to lose their lubrication, and eventually it's going to stop spinning. And once it stops spinning, I told you the purpose for the spinning was to dissipate the heat so that you don't melt your anode. So if it stops spinning, then what do you do to your anode? You melt your anode. So there's two different ways that it's going to destroy the tube. Another way, and we're going to talk about these again later in the semester, I'm just trying to make the point that heat is bad. It's both good and bad in the X-ray tube. One other way is that if you walk into the room, your X-ray room's hot or cold? All the time. Cold. Yes, I'm freezing. They're cold most of the time, right? So let's say you know, you walk in off grave shift. You're making the first exposure of the day, and your first patient is 600 pounds. Do you think you're going to see some 600-pound patients?
Yeah.
You absolutely will. Okay, your first patient, 600-pound patient, and you're shooting the abdomen on them. How many X-rays do you think you're going to have to make to get a good abdomen on a 600-pound patient? A couple, yeah. Yeah, you're going to make a lot, right? So what that means is this is going to have to get really, really hot. But your X-ray tube's been unused all night long in a cold X-ray room. What do you suppose it feels like on the inside? Probably cold. Now we have some safety things in place to prevent that from happening within a normal range, but if you get those weird big patients, huge patients, your first exposure is on that patient first thing in the morning, you're going to be creating a lot of heat on a cold glass tube, okay? Yeah, you know where I'm going with this. Your windows all iced up in the wintertime, you throw hot water on it, don't you? No, you don't, unless you want to replace your windshield. So you put cold water on it, and you know, you get the windshield wipers going pretty quick before it freezes back up. So a lot of heat, first exposure in the morning, what might happen to your X-ray tube? It shatters, right? So I go all this way to say about 99% of what we create in the X-ray tube, what do you think it is? X-rays? No, it's heat. Yeah, so it really depends on the KVP level that we use, and we'll talk about that later in the semester, but upwards of 99% of what we actually create inside the X-ray tube is heat. A little bit of light, even fewer X-rays. So really inefficient is what it is. It's the most efficient way we have of creating X-rays as of yet, but it's still very, very inefficient. But we'll tell you, I'll tell you later in the semester, it's a numbers game. We're going to use a lot of amperage, even though it's milliamperage. And we'll define what an amp is later in the semester. It's a lot of electrons. Even at milliamperage levels, it's a lot of electrons. So I'll break that down later in the semester. Okay? So any questions on type of, thank you, energy that we use.
That's our
Aren't
fun.
some envelopes metal though?
Yes, very good.
Read ahead, or yeah, okay, very good. Some, and that's why. One of the reasons why is that some of the, when we talk about the envelope, what we're talking about is the tube itself. Okay, so in a lot of, we've got some upstairs that I'll get a cart and bring down at some point, but in a lot of your tubes, most of your tubes that I've seen anyway, that's all glass. Okay, but some are made of metal, and that offsets some of that. Very good, very good. Okay, any questions on that? Okay, then now we're going to get kind of into Einstein. If you look over on page 5, matter and energy are interchangeable, and it's kind of hard to wrap your mind around, his whole theory of relativity and how it, And you can see it in action, but the actual calculation, you're not gonna have to, one, you're not gonna have to work that out, and two, it's kind of hard to see. Because you see something like an atomic explosion. What do you got going on there? Yeah, you got small pieces of matter making a ridiculous amount of energy, right? And then you're sitting around a fire and you cut down this great big tree and you throw it in the fire, and you got a massive piece of mass creating, you know, pretty good fire, but is it anything like a nuclear explosion? The answer is no. You know, so for you know, reasons that are beyond the scope of this class, just understand that they are interchangeable. So again, you know, you plant the seed of an oak tree. What happens to that seed? Hopefully, it's gonna pop open. It's gonna grow seed or grow roots. After it grows roots, it's gonna grow trunk, right? It's gonna absorb some of those nutrients, and through chemical process, it's gonna create matter. It's gonna grow into a tree. The tree dies and then falls down. What happens to it? It decays. It decays. It decays and it becomes food for the next tree, right? Or if you cut it down, I've got a fireplace. My wife loves a fire, so you know we buy or you know we live on some property, and sometimes we'll have a tree fall. We'll cut up the tree, split it up. We dug a pond, so you know they took down a lot of trees, split a lot of wood, put it in the fireplace, and make fire out of it. So that's matter to energy, energy to matter. Photosynthesis, you know, the sun, the plant absorbs, you know, some of the energy from the sun and it grows. That's energy to matter. Okay, so they're interchangeable. And Einstein is the one that, you know, kind of defined that mathematically with this theory of relativity. So we take a little bit of a turn at this point and talk about radiation. Just there's no segue into the discussion of radiation. It just suddenly pops up that radiation is radiation. So what is radiation? Just transfer energy, right? Is all radiation bad? No. You know, you can say that the sound that you're hearing is radiation. It's vibration of molecules, so it's a little bit different than what we actually think of in radiation. But, you know, it's kind of the same principle, right? Now, you can make the argument that I sound too East Texan, and that's bad. But, you know, is it harmful to you? No. Anybody ever been to a concert and sat right next to a speaker?
Yeah.
Yeah. I went, there's a bunch of us went to a concert. It was at the Toyota Pavilion up in Dallas, and we were way too close. My wife went out to the lobby or the entrance area. They were selling, or you had to sign up for something. She used my email address and hers to get us earbuds to stuff in her ears because it was just too loud. It was miserable loud. So anyway, if you get too close to it, it gets too loud, it becomes harmful. Same thing with a lot of different types of radiation. Light is radiation. Is that light harmful? No. Could it be harmful? You ever taken a magnifying glass in the sun or any kind of light? What can you do with it? You can focus it and you can burn things. You can burn ants and, whatever. You can burn things with it. So you can focus the light and it becomes bad. Right? So the type of radiation that we create, which is electromagnetic energy, is with a high enough energy level that it can ionize an atom. Okay, so what's an ion? Charged particle, right. So if you have a neutral a neutral atom, particle, how can it be ionized? You got positive charges, negative charges. You'd have to add or remove one of the two of those, right? So the proton locked inside the nucleus of the atom is very difficult to dislodge. We're going to talk about when that happens, and we've got nuclear energy when that happens, but we'll talk about that later in the semester, maybe in the next chapter. But the easier thing to do is to knock around electrons. And you see that happen, or you feel that happen all the time. We talked about that a little bit the other day. It gets cold outside, and it's easy to build up static charges, right? You walk across a carpet, and you can create a static charge, and you get close enough to something, and that spark jumps. That's just movement of electrons, okay? So, that's ionization, essentially. You know, you're scooping up electrons and you're depositing them somewhere else. With ionizing radiation, what we have is a radiation level that's high enough that it can remove one of those orbital electrons. That becomes a little bit dicier. And we talked about that on Wednesday. You know, if it removes, an electron, that electron becomes free radical. This time next semester, or next year, you're going to be doing experiments to prove or disprove the things that we talk about in class. And I find it to be fascinating. I find it to be fun. I give the students a lot of latitude to pick the different things that they want to do. You know, I've got some parameters. I say, okay, you know, these are suggested topics, but if you come up with something, you know, come talk to me. We'll talk about seeing if we can, you know, if you got a viable experiment. So I had two students come by yesterday. They're working in groups of 3. I had 2 students come by yesterday, and if you take pure water and you expose it to enough radiation, ionizing radiation, you can make hydrogen peroxide. And that's what they want to do, is get some test strips, take a quantity of water and shoot it a few times and dip the test strip in it, see if they can make some hydrogen peroxide. I don't think that they're going to be able to do that without being harmful to the x-ray tube. So I told them, you know, if it gets to high levels of exposure, don't do that on my x-ray tube. It's brand new. And it's got to last until I retire. I mean, we wound up with almost $300,000 worth of construction equipment. I'm not going to get that again, you know, for another 10 years, and I don't want to be here another 10 years. So, you know, be gentle with my x-ray room. You know, it's the only one I've got until I retire. So, ionization, removal, and you can, in that removal of the electron, you could cause some damage. Okay? So, ionizing radiation is electromagnetic radiation in this case, with a high enough energy that you can remove an orbital electron and thereby create an ion. And really, fundamentally, what you create is what we refer to as an ion pair. Ion pair? How's that? Well, you've got a nucleus, and you got an electron. You knock that electron out. Well, you got one electron. What do you have? Hey, what's the overall charge of that atom? You have one proton, positive charge, one electron, negative charge. What's the overall charge? Neutral. Neutral, right. They cancel each other out. Now, I'm going to change that because this is X-ray photon. And I'm still locked into, you know, electrons hitting electrons. So if this comes in with enough energy to knock that thing out, now what's the charge of your atom? Positive. It's positive. What's the charge of your electron? Negative. Still negative. So how many shoes do you wear?
2.
We call those a pair of shoes, right? So you have an ion pair. You've created 2 ions, a positive ion and a negative ion. That's ion, excuse me, ion pair. Okay, so after, this is going to happen to me and Amy both, probably less so her. In summer, I have no speaking classes. One is just all tests where I don't have to say a whole lot, and one is an online class. So when fall rolls around, my voice is not used to speaking that much, and you're going to get this, you know, I'm going to sound like I've been on whiskey night every night for probably the next 2 or 3 weeks. Okay? So if my voice cracks, that's what that's all about. All right, so what's our time? 10:10, but we're at 20 minutes left. Okay, awesome. Awesome. We're right at an hour. So, and we're going to finish early. But sources of ionizing radiation, on page 5. So it sounds kind of scary. We got all this ionizing radiation. You know, you want to stay out of the X-ray room. And if you stay out of the X-ray room, you're never going to be exposed to ionizing radiation, right? No, no, not even close. You're getting blasted by ionizing radiation everywhere, okay? So just looking at the chart on page 6, and sometimes especially in Merrill's, you know, it's an easier read if you start by looking at the pictures and then go into the text, and you'll figure out what it is that you need to know about every projection. But if you start by looking at the pictures and picking up what you can see in the pictures, and then go over and read, then you can say, yeah, I saw that, yeah, I saw that, yeah, I saw that, right? So sometimes it's easier to do that. So if you look at the figure on page 6, what you see is source distribution of background radiation, and what you'll see is radon. There's ionizing radiation and radon. You ever heard of radon? You know where radon is found? Everywhere. It's found everywhere. Sheetrock, cement is found everywhere. Okay, if it's ionizing radiation, you're inside of a building right now. Are you getting hit? Yeah. What do you suppose is covering the wood studs in the walls of your home? It's sheetrock. It's gypsum. Gypsum is full of radon, or emits radon. You're getting hit even if you're at home. Okay, if you're walking around outside, you're getting hit by ionizing radiation. Where's it coming from? Well, let's look back at the chart. What does it say? We'll skip over other, but thorium, potassium, radon, terrestrial. What does terrestrial mean? Extraterrestrial means from space. Terrestrial means right here, right? So maybe radon, maybe something else. And then the second biggest category is from not terrestrial. That would be extraterrestrial, is from outer space. The sun creates X-rays, and they hit you all the time. Okay, it's not just light. It's all kinds of stuff that's coming from the sun, including X-rays. Okay, so you're getting ionizing radiation from all different types of sources. If you look on page 7, you'll see they really need to increase the size of the font on these. My eyes aren't that good anymore. Percentage of diagnostic and interventional medicine, radiation exposure. So what's the biggest one? CT. So we get a lot of exposure from CT. Nuclear medicine is next, followed by diagnostic radiology, and then you've got cardiac, catheterization, and then non-cardiac interventional are about the same size. So what that means is that most of the radiation exposure that we receive really is not from even your clinical education. If you're a patient, the quantity that you're going to receive is very low. Okay? Even if you're a radiation worker, it's going to be higher than your average patient most of the time, but it's still going to be low. So you got that little radiation detector, right? We refer to that as a TLD. And what that does is, you know, you're supposed to wear it on the outside of your apron so that we actually measure your dose, not the dose under the apron. So what happens with that thing is we take it about every 3 months and we send it back to the place that we contract with to read those. And they heat those up. Those are what we refer to as a thermoluminescent dosimeter, TLD. So when they, heat the crystal up that's inside of there, it emits light. Thermoluminescent, hot, gives off light. Okay, it's thermoluminescent dosimeter. And they measure the amount of light that comes off of that so that, you know, we can tell how much it absorbed in radiation, so we can tell how much you absorbed in radiation. Okay, that's how those things work. You're going to get exposed to ionizing radiation. It's going to be at such a low level that it's not going to come close to the natural background unless you do something really goofy. And most of the time, it's going to be at a level that's so low that the TLD will show 0 or possible M, meaning minimum. meaning that the dose was so low that they couldn't detect anything. Okay? So, here's the thing, though. You are going to get exposed to ionizing radiation. You can't get around it. You're going to get hit. There are certain exams that are going to be higher dose than others. If you're in a fluoroscopy room, you know, you're just going to get exposed. You've got to be in a room with the patient while the X-ray beam is being energized. You can't get around it. You got to be in with the patient. If you don't have to be in with the patient, where should you be? Not in the room with the patient, right? So you want to step out of the room in as much as you can. If you're doing portables, you want to move away from the patient as far as you can. Part of the reason batteries are so heavy is because the chemistry inside the battery, you've got a lot of fluid in there, but you've also got lead, okay? So what are your aprons made of? Lead. Yeah, it's lead impregnated vinyl is what it is. Got a little bit of lead in it. But behind that control panel, the glass is leaded glass. You can tell that it's not as clear as some of your glass at home. It's because it's got lead inside of it. You're doing portables where if you can't back up far enough and around the corner to get away from potential scatter radiation, what's your other option? Get behind that leaded battery pack, right? Stand behind that. If you don't need to be in the room with the patient, get out of the room. So if it's just a shoulder x-ray, patient's on the table, is there ever a reason for you to be in the room with that patient? The answer is no. Unless they're in danger of rolling off of the table and somebody has to hold them on the table, there's no reason for you to be in the room, right? You gotta be in a room with fluoroscopy exams, can't get around it, but 90 or more % of the exams that we do, you don't have to be in a room. Get behind the glass, right? And that's really pretty much all I've got for you today. I'm going to talk about, I will just drop this, and Amy's probably already talked about it. How do you minimize your radiation dose? And I've kind of touched on most of those already. I just didn't sum them up. 3 things. Has Amy touched on them?
Energy,
Time, distance, shielding. The shielding's a lead apron. Time is spend as little time around the energized X-ray, tube as you possibly can, and get away from the tube as far as you can, or really is away from the patient as far as you can, from the radiation emitter. So you're not going to be shot directly by the X-ray tube. Your dose is going to come out of the patient. Okay, so we'll talk about the significance of that later. But time, distance, shielding: stay away from, out of the room, behind. Some sort of barrier. Time, distance, and wear your lead apron if you have to be in the room. So yesterday, I recorded a couple of things and I got one posted. It takes a long time to edit. Y'all don't know how weird it is talking to an empty room. It really is strange. And you start something and you go, I don't want to say that. And you start something else, it's like, that sucked too. You start something else. I mean, if I record a 15-minute video that's not in class, is probably 30 to 45 minutes worth of talking, and then in that is probably 2 hours worth of editing. Okay, so it's a thing, right? So I recorded 2, only had time to get one posted yesterday, and 2 skills that you really should work on hard early on so that you can move on to more important stuff is what that console means. If tech tells you to go set up for a chest x-ray and you go, what does that mean? How do I do that? Well, now you're off to, let me go show you again, I would recommend, I'm going to get the other one posted, I hope today. I'll have to edit this one, and there's not a whole lot of editing due to it, but I'll get it posted today, and it may be tomorrow, maybe, before I get the other one posted. But the other one is manipulation of the X-ray tube, because the thing that you're going to do probably that's going to irritate techs more than anything else is this. So When you're setting up for an x-ray, you know, you got the patient on the table. First off, get the x-ray tube out of the way. Move it out of the way. Otherwise, the patient's going to hurt themselves on it, right? So get it out of the way before you get the patient in the room. Get the patient on the table. Let's say we're doing an abdomen on the patient. Get the patient onto the table. There are specific places where the x-ray tube is going to lock in on the ceiling and at a distance, okay? So your steps are get the patient on the table, grab the tube, put it, lock it. When they say lock it in, what they're talking about is put it in a place where it's aligned to the table, okay? So again, we're working off the table, but the same thing applies to the wall bucky. Lock it in means going this way. Lock it in also means getting the height right. What are our two distances? 40 and 72. So if they're on the table, your distance is 40, right? So lock it in crosswise, lock it in, you know, vertically. And then what you want to do is you want to line the x-ray tube up with the image receptor. So you got to pull the tray out a little bit and line the two up. Now this is where you're going to make the mistake, is that let's say you're doing an abdomen on the patient. Your image receptor is here and the patient is here. What you're going to have a tendency to want to do, you know, the light field is off-centered on the patient. What you're going to have a tendency to want to do is grab that x-ray tube and line it up over the patient. Okay, so when you do that, what are you going to do? Well, that's one. But you're going to take it out of detent. You're going to take it out of being locked in, okay? But that's going to be your natural default setting, is to grab the x-ray tube and move it. And slap your own hands when you do that, because you've already locked into the table and you got your distance right, and you've already lined up your x-ray tube to the patient, or to the image receptor. What does the tabletop do? It floats all over the place, right? So lock it in, line it up, and then move the patient in that order, okay? And if you can master that, just, you know, you don't even have to have a patient in the room. If there's two of you at a clinical site, you know, take each other into the room and practice doing it. Don't shoot each other, but practice doing that, right? And the quicker you can get that down, the fewer chewing outs you will get. I guarantee it. Learn to set up your control panel, learn to set up your room, and then you can move on to actually focusing on, you know, because you get chewed out. You know, somebody says, I showed you this over and over. You watch those videos and listen to them until your ears and eyes bleed, until you get it locked into your own head. You know, quicker, you know, you get chewed out, you have a tendency to not focus for a while, right? So if you can get those two skills mastered quickly, then you can focus on, you know, developing your skills, taking exams. Okay? That's all I got for you. Any questions? All right, you made it through the first week. We didn't lose anybody. So hopefully everybody shows up on Wednesday. Remember, Monday's a holiday.